Can water extinguish the sun? Watch what happens when 400 sextillion tons are poured on it. In the vastness of the mysterious universe, the sun shines like a brilliant pearl, emitting endless light and heat as the core and master of our solar system. Yet, a seemingly absurd question arises: can water extinguish the sun? The answer, unequivocally, is no. Even with an immense volume of water, the sun cannot be doused. To delve deeper into this intriguing query, let's explore a hypothetical scenario. Imagine pouring 400 billion tons of water onto the sun. What catastrophic changes might occur? According to scientific estimates, the mass of the sun is approximately to by 1,030 kilograms, equivalent to about 200 billion tons. Therefore, pouring 400 billion tons of water would almost double the sun's mass. One might intuitively think that such a massive volume of water could extinguish a flaming fireball like the sun. However, the sun's energy generation mechanism differs fundamentally from common combustion processes we encounter daily. It is driven by the intense nuclear fusion occurring within its core. Scientists have determined that the sun's surface temperature reaches about 5,500 degrees Celsius. In such extreme heat, even a small amount of water would not exist in liquid form. It would vaporize instantly. The water molecules would be ruthlessly broken down by the intense heat into hydrogen and oxygen. However, when considering 400 billion tons of water, the situation changes drastically. Although the sun releases enormous amounts of heat, it would only convert a small fraction of the water to gas. Most of the water would quickly condense under the sun's gravity, forming a thick layer of water surrounding the sun, reaching hundreds of thousands of kilometers in thickness. This sudden water layer would significantly influence the sun's surface temperature, causing it to drop sharply. To an observer on Earth, it might appear as though the sun had been extinguished. However, this is merely a surface-level illusion. The core's nuclear fusion reactions would not stop simply due to the presence of this outer water layer. To understand this phenomenon, we must recognize that the conditions necessary for nuclear fusion require a sufficient amount of heat, primarily generated by the sun's own gravity. The heat that fuels the sun's fusion reactions arises from the gravitational collapse of its mass. The sun's internal structure shows a temperature gradient, where temperatures increase from the surface to the core. The core reaction zone is where fusion occurs, and if a layer of water were to form around the sun, it would not cool the core. Instead, it would add mass, intensifying the sun's gravitational pull and consequently its internal temperature. As the sun's mass increases due to the added water, the temperature within the core would rise dramatically, allowing regions outside the core reaction zone to cross the threshold for fusion reactions. This would lead to an expansion of the core reaction zone and an increase in the rate of fusion reactions, significantly enhancing the sun's energy output. Based on models of stellar density, if the sun's mass increased by 400 billion tons, its energy output from fusion could surge by approximately 70 times. Under this influx of energy, the outer water layer would rapidly vaporize, transitioning into a plasma state and further decomposing into hydrogen and oxygen. This oxygen would become part of the sun's material composition, while the energy released from the core would create a barrier, preventing these new elements from directly participating in fusion. Consequently, the sun would not extinguish, but rather evolve into a hotter, larger star with a surface temperature exceeding 10,000 degrees Celsius. This transformation highlights a critical aspect of stellar dynamics. The greater a star's mass, the more quickly it consumes its nuclear fuel. Thus, as the sun's mass increases, its lifespan would shorten significantly, likely evolving into a red giant star within tens of millions of years. In this phase, the outer layers of the red giant would shed material, culminating in a stunning planetary nebula, with the remaining core eventually evolving into a white dwarf. Even if we were to pour 400 billion tons of water onto the sun, it would not be extinguished. Instead, it would undergo a series of intense transformations, ultimately rebirthing as a brighter, hotter star with a shorter lifespan. If we extend this hypothetical scenario further and consider adding even more water, resulting in a sun exceeding 8 times its original mass, we would witness extraordinary and violent changes. This could lead to a cataclysmic supernova explosion at the end of the sun's life, one of the most spectacular phenomena in the universe. In exploring the interaction between the sun and water, we must go beyond surface-level observations and delve into the underlying scientific principles at play. This interaction serves as a grand cosmic spectacle, illustrating the transformation of matter under extreme conditions and the potent release of energy. Water molecules, subjected to the sun's heat and pressure, would undergo a dramatic transition from stable structures to plasma, reflecting the inherent vulnerability and variability of matter under intense energy. From the perspective of stellar evolution, this thought experiment provides a unique lens through which to examine the life cycles and evolutionary paths of stars. Star evolution is typically viewed as a slow and stable process influenced by initial mass, chemical composition, and internal physical processes. However, significant external factors, such as a large influx of water, can dramatically alter this evolution. The interaction between the sun and water, and the resulting changes, emphasize the importance of considering both intrinsic stellar characteristics and external environmental influences in the study of stellar evolution. This knowledge is crucial for understanding the universe's broader material and energy cycles, which play a pivotal role in the formation of galaxies and the birth of new stars and planets. By investigating these complex interactions, we can deepen our comprehension of the universe's laws of conservation and transformation of matter and energy. Such inquiries not only enrich our understanding of celestial bodies, but also stimulate our curiosity about the mysteries of the universe, ultimately pushing the boundaries of human knowledge. In summary, while the notion that water could extinguish the sun seems whimsical at first glance, it reveals rich scientific insights and profound philosophical implications. Through rigorous research and theoretical analysis, we gain a deeper understanding of the sun's essential characteristics and our place in the universe. In the quest for scientific truth, seemingly absurd questions can lead to groundbreaking discoveries, expanding our understanding of the cosmos and revealing the intricacies of existence.